Hello and welcome back to Digital ASIC Design. Now we're going to start actually getting into the Verilog language and how to design with it. We're going to do this through a complete small example. This module is actually broken into 4 units, which are further broken into submodules for the purposes of producing these videos. The first unit is just an introduction to HDL design with Verilog, just to motivate the basic features in the Verilog language that compose its synthesizable subset. The next unit is a complete example, a simple counter, showing how we design, translate that design into Verilog, and verify that design. The third unit is about the actual verification and synthesis. How do we manage the synthesis tools to manage timing and achieve the goals we want in synthesizing the design to a netlist? And final unit are some further examples. This first unit is an introduction to design with Verilog. All I'm going to do is just motivate the basic features in Verilog in the synthesizable RTL subset and just introduce you to the language overall. The references are given at the bottom there. I remind you of our course mantras, because this module is going to get into the next 2 mantras. 1 clock, 1 edge, flip-flops only per module. Design before coding, which we'll get into in the next unit. And behavior implies function, which is what I'm going to start introducing to you here. The final mantra we won't get to for a few lectures' time. So I'm going to describe you the 3, and that's it, the 3 coding styles that make up RTL. That is the synthesizable subset of Verilog. I'll briefly contrast VHDL to Verilog, and finally describe the basic structure of a Verilog module. So the reason approaching the course in this way is because rather than going through the language, learning it feature by feature, and then using how to do design, I want to integrate design and coding together and introduce you to the features in the language in a design-motivated fashion. Because I want to emphasize that design is more important than coding. This is more so true in RTL-based design for hardware than it is in writing normal software. I also want to emphasize how you can read the Verilog language by simply reading it, inferring the behavior that's being described, and then thinking about the logic structure that matches that behavior. And by doing this, with a few little additions about understanding the syntax and the meaning, you can read RTL fairly straightforwardly. And these are the references. So let's get into it. The reason why we have hardware description languages is to capture a logic design intent in register transfer language form. What that means is all the registers are specified, all the outputs of the registers are named. However, I say logic intent because we don't have to describe the non-register logic down to the gate level. We can describe its behavior, we can describe higher level functions, and let synthesis work out and optimize the detailed combinational logic. So the idea is that once we've written the design intent in RTL, we can simulate it to verify correctness, and pass it through a synthesis tool to get reasonably optimal gate level design that meets timing if we designed it reasonably and have reasonable objectives. When this methodology was introduced in the early 90s, it dramatically increased designer productivity. Before that point, chip design was done by pushing polygons around in a CAD tool, and before that with pieces of mylar, in order to create the layout, which then became the masks to go to fabrication. I.e., all chips were done using the full custom methodology that we talked about briefly in the introductory notes. This was very slow. So the introduction of automatic synthesis and hardware description languages that go with it increased designer productivity by several orders of magnitude. This in turn enabled us to design chips that otherwise would not have been worthwhile design, and then in turn, very quickly actually, opened up, it led to the creation of companies like Cisco to create the internet, at least the high capacity form of the internet that we're familiar with today, and companies like Qualcomm to create the chips for mobile handsets that led to the mobile computing revolution that we're still going through today. And you can argue this was a critical technology, of course on top of other technologies, the enabling semiconductor technology, but this is a critical technology to allowing those chips to be designed, because without this methodology, we could not have afforded to design those chips, at least to the complexity that we have designed them. So the key step that follows design at the RTL level is synthesis, which we won't get to until the next unit. But really, synthesis is not a magic button. I do want to emphasize that synthesis is a combinational logic optimizer that's timing aware. It cannot turn a bad design intent into a good design intent, and it certainly cannot eliminate unneeded registers or add registers if they're needed. So let's introduce you to one basic Verilog construct, that is how to describe a flip-flop. Now if you think about it, and were asked to describe the behavior of a flip-flop in English, you would say something like this statement here. Let's see, for every positive edge of the clock, Q becomes equal to D. That's the behavior of a flip-flop in English. Well, of course, code is just logically precise English captured to a formal syntax. So let's capture this behavior as code. For every positive edge. Let's make that always at. So that's for the every part, always. We've got always instead of every. And always at pos edge clock. So for each and every pos edge on the clock, execute the following. Q becomes equal to D. Don't worry about this funny less than or equals to this point. This is a form. This statement is actually a form of assignment. The reason for this particular form of assignment we'll come back to in a later class. So this introduces the always at statement in Verilog. That is, this is a statement that triggers the execution of the block that follows it when the items in the sensitivity list provide that trigger. In this particular case, that trigger is the positive edge of the clock. So for each and every positive edge of the clock, this code block gets executed. This leads us actually to an illustration of mantra number 3. Let's turn this around. Let's say you saw this statement here and had to tell me what piece of logic is being described by this statement. Well, there's only one gate who has this functionality of only changing on clock edges. And that gate is a D flip-flop. So this piece of code describes the behavior of a D flip-flop. And in fact, it's the only way to capture D flip-flops in Verilog language using RTL. Let's contrast that with this piece of code. Always at clock or D if clock is high, Q is equal to D. Well, when you don't have edges in the sensitivity list, what it is meaning is when they change. So this statement, if clock, then Q equals D, gets executed every time clock or D changes. So the piece of logic being described here may or may not change whenever clock or D changes in either direction, up or down. And when that changes, what actually happens is the behavior, if clock is high, Q becomes equal to D, with the implicit behavior of if clock is low, what is going to happen? If clock is low, then Q will stay the same. What gate has the same behavior as the code described here. That gate is a level-sensitive latch. That's exactly its behavior. Q is assigned to D, Q follows D when clock is high, and whenever clock or D changes, Q only changes if clock is high. So every variable that is assigned in a block, starting with always at pos clock, always at neg clock, becomes the output of an edge-triggered flip-flop, whether you meant it to or not. And this is a big reason why I emphasize design before coding. A lot of people try to approach this by writing C, then slapping around a bit of Verilog to turn it into Verilog by throwing in some trigger statements such as these, without realizing what they're doing is building a huge number of flip-flops. It's up to you, the designer, before you write code, to decide what should be the output of a flip-flop. So that brings us to the end of this particular submodule. The 2 points I was emphasizing, that what we're going to do is use Verilog to capture a design intent at the register transfer level, which again means we have to specify all the registers and then describe what's transferred between them. There's the logic. And I remind you very explicitly that all variables assigned after an always at pos clock statement become the outputs of flip-flops. And why is that? Behavior implies function. That statement describes the behavior of an edge-triggered flip-flop. Hence, the function being captured is an edge-triggered flip-flop. Now what I'd like you to do is do the submodule quiz before proceeding to the next submodule within this unit. Thank you very much.